my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on EDEXCEL, topic 12, acid-base equilibria. So this video is all to do with acid-base equilibria. There's quite a lot of stuff in this topic, but we'll go through all the information that you need for this, and it is dedicated to EDEXCEL as well. So if you are studying EDEXCEL A-level chemistry, then this video is exactly what you need, because it has everything that you need to know and nothing more. So you won't run through this and think, oh, do I need to know that, and is that on my exam, etc. Well, anything in here is specifically tailored to EDEXCEL, so you'll be safe with this video at least. So the videos, I have a full range of videos for EDEXCEL chemistry from year 1 all the way to year 2, so it's very comprehensive and tailored to EDEXCEL. They're all for free, they're all found on Allery Chemistry YouTube channel. Please go and have a look on there. All I ask is that you hit the subscribe button to show your support, and that would be fantastic. Because it does take an incredible amount of work to put all this together. So all I need in return is just for you to hit the subscribe button, and so long as people subscribe and watch the videos, I will keep on making them for free. Also, if you would like to have access to this PowerPoint for your own use, so you can print it off and look at it in your own time on your on your smartphone or your tablet on the move, you can print it off, use it as your revision notes, etc. Then they are available to purchase. If you just click on the link in the description box below, click on that, and you'll be able to have a look on there. They're great value for money, but just have a quick look there. Also, this video looks into the for revision purposes. So you may have done this topic already in school or college, or you're working independently. So it is designed for revision. So I'm going to go through all the information that's required for that purpose as well. But it's just as important to practice exam technique as well. So once you've had a look at this video, have a look and see if you can do some of the questions. If you're not sure, if you've done a past paper question and you're not too sure on the answers, or you need a refresher, then come back to this video, go to the bit that you need, and then that would integrate it within your revision. So it's another way of revising, that's all. But also, I have done some past paper walkthroughs on Allery Chemistry YouTube channel, so go and have a look. See what you can find. There's new things added on all the time, so it's kept up to date. So go and have a look on there. Okay, so like I say, this is dedicated. This is a big old topic, this, and there's a lot of calculation here. So get your calculator buttons warmed up. But anyway, we're going to look at everything that's dedicated to EDEXCEL, like I say. Okay, so let's start with Brønsted-Lowry acids and bases. So Brønsted-Lowry, these were two chaps who, two chemists who basically came up with a theory to explain how acids and bases worked. So you had Thomas Lowry, who is a Brit, and he's on the left there, and Johannes Brønsted, who was Danish, and these two got together and decided to come up with an acid-base theory, as you do. So there's the pictures there of the two. The theory they came up with is that acids are proton donors, and you're going to see this a lot throughout this topic. But that's their specific theory that they came up to, because there were other theories as well, surprisingly. But this is the one that you're going to mainly focus on here. So when we mix acids with water, hydrogen ions, H+ ions, are released. Okay, so the acid dissociates. So what they actually form when we take an acid, it actually forms something called a hydroxonium ion, which is H3O+. And it's these ions that make the solution acidic. But for simplicity, what we'll use is H+ ions. And you'll see that a lot in the equations. But just be aware that actually, in reality, it is the hydroxonium ions, also known as hydronium ions, H3O+, that makes it acidic. So here's an example. I'm using the hydroxonium ion here. So HA, you'll see this used throughout the video. HA is used to represent an acid. Plus H2O will form H3O+ and A-. So that's what happens when we add an acid to water. It dissociates and forms, and obviously forms the products that you can see there. Brønsted-Lowry bases, these are proton acceptors, so it's all to do with the proton, as you can see here. So when we mix bases with water, they react with H+ ions to form hydroxide ions, which are OH-. And here's an example equation here. So we've got B, and you'll see this throughout the video as well. B is used to represent a base, plus H2O, and that'll form BH+ and OH-. So remember, what makes something basic in terms of what would a basic solution look like. It means you've got a large amount of OH minus ions in there, more OH minus ions than you do H plus. So these are the key ions that we're going to be looking at all the way through. Okay, so let's look at some examples of acids and bases. And what we need to be aware of is we need to be aware of acids can be strong and weak, and so can bases as well. So we're going to look at some different examples here. So when acids and bases react with water, they're a reversible reaction. So you can see, just as we've seen before, acids actually form, and you can see here, acids form H3O+, that's your hydroxonium ion, or hydronium ion is produced. Bases produce your OH minus ions, and that's what makes it basic. Remember, bases are symbolized with a B. So strong bases dissociate or ionize almost completely, and you'll see some of the assumptions we'll make later on in some of the calculations where we see that bases, we assume they dissociate fully, and weak bases don't, they dissociate poorly. Likewise with acids, strong acids dissociate fully or ionize, and weak acids dissociate poorly. Sorry, that should say weak acids on there, okay? So that should be weak acids dissociate poorly. So let's have a look at a weak acid example. So a weak acid is something like ethanoic acid, which is a carboxylic acid. So these are a weak acid, and what this means is, from an equilibrium point of view, is that if we have a look at our reaction here, so here's our carboxylic acid, in this case we use an ethanoic acid, it's in equilibrium with the ions, obviously it dissociates, but because it's a weak acid, equilibrium lies well over to the left. So we don't have much of these, but we have a lot of these. So weak acid is generally a poor ionizer. It doesn't dissociate very well. That's going to be very important when we look at things like buffers, for example, which is towards the end of the video. You need to be able to understand how acids and bases and weak and strong acids link up with equilibrium, because that's going to be vital all the way through this video, but particularly for buffers. So strong acids, these are like mineral acids such as hydrochloric, nitric and sulfuric acid. These are dissociate readily, very strongly ionizing. So for example, here's hydrochloric acid here, as you can see. It's in equilibrium, it forms your H plus ion and chloride ions as well. So these dissociate readily. We assume that we don't have much of this, and we have a bucket load of these ions here. So we have a large amount of H plus ions, and that's what makes it a strong acid. Strong bases, so these are examples are things like sodium hydroxide, excuse me, and potassium hydroxide. And so these strongly ionize, they strongly dissociate, just like strong acids. They produce large amounts of Na plus and OH minus ions. We don't have a large amount of sodium hydroxide, so equilibrium lies well over to the right in this example here. And weak bases, now a particular example you need to know for weak base is ammonia, which is NH3. Now ammonia is a weak base because it dissociates poorly, but what makes it a little bit strange with ammonia, and you'll see this later, is that ammonia doesn't actually have an OH group, unlike a strong base. So what it needs is it relies upon water solely in this. I mean, all bases do, but particularly ammonia, it relies upon water to actually produce the OH minus ions to make it basic. So, for example, you can see here, there's your ammonia reacting with your water to form your ammonium ion, which is NH4 plus, and it's also forming your OH minus ion. It's a weak base, so what that means is we don't produce many of these ions here. We have a large amount of ammonia and water. Obviously, water is what you add to your ammonia, but to make it into a solution. But it's a weak base, so that means it doesn't dissociate fully. So these are your strong bases along the bottom there, and these are your strong acids, which are along the top. But like I say, I'll get that changed with the strong acid, because that should say weak acid, of course, because they dissociate poorly. Okay, so let's look at some conjugate pairs or conjugation. It sounds like a very difficult word, but it's not too bad. So a conjugate pair is linked by the transferring of a proton. Okay, so this linked with the Brønsted-Lowry theory that we've just seen before. So any species that has gained a proton is the conjugate acid of a species that has lost a proton, which is the conjugate base. Okay, so we're going to have a look at some examples here. So remember, the Brønsted-Lowry acids and bases react according to the following equation. So remember, you've got your acid, which is your HA. They react with a base. We give base is symbolized by a B. That forms BH plus and A minus, as you can see there. So HA is an acid in the forwards direction because what it's doing is it's donating a proton to form your BH plus, as you can see there. So this proton here is now actually attached to the B, which is the base on there. So that is definitely an acid. And A minus is a base in the reverse direction as it accepts a proton from BH plus to form HA, if you see. So if you go backwards, A minus receives that H plus to form HA, which is your acid. So what we have here is a conjugate pair with HA and A minus. So we've got the conjugate acid, which is HA, and the conjugate base, which is A minus. So it's probably easier, as you can see, to actually draw diagrams like that because it helps us to see which is the acid and which is the base. But these are paired up. And likewise, we also have a conjugate pairing with B and BH plus, where our conjugate acid is BH plus because remember it's donating the proton to the A minus, and the conjugate base is obviously B because going in the forwards direction, B is accepting a proton to form your BH plus. Okay, and our black arrows on that diagram symbolize or show our conjugate pair. So water reacts with acids as well to form H3O plus, that's a hydroxonium ion or hydronium ion. So they could be called either one of them. So that is a conjugate acid because it reacts with the base to form the conjugate base, which is OH minus. So for example, we can see here your B reacting with water to form BH plus and OH minus, and our acid HA reacting with water to form the hydroxonium ion or hydronium ion H3O plus, and your A minus as well. Okay, so let's look at some acid-base reactions. So when acids and bases react with each other, then protons are exchanged. So the key thing here, as the Brønsted-Lowry states, it's all about this proton. Okay, is it being received or is it being donated? And that determines whether it's an acid or a base. So let's look at this generic example. This is HA. This is your acid here, remember? So HA donates the proton to the base, which is the B, and positive negative ions are produced as we've seen before. Now you'll remember this from year 1 chemistry. Remember this reaction is in equilibrium, and if we add more HA or B, whatever that is, because they're on the left hand side, these are your reactants, then it will then equilibrium will shift to the right to use that up as Le Chatelier's principle, so if you remember that. And on the other hand, if we increase BH plus or A minus, which is on the right here, as you can see there, this will then the equilibrium will shift to the left to use that up. So remember, this is Le Chatelier's principle that we're looking at. So water behaves as a base when acid is added to it. Okay, and you can notice, notice in this reaction that the water molecule has accepted a proton to form your hydroxonium or your hydroxonium ion. So this is obviously this is in the previous reaction that we've seen here, not particularly in this reaction, but it accepts that H plus, as you can see. So this is the reaction here. So you've got your HA plus your water will form your hydroxonium ion or your hydronium ion plus your A minus. So this is the reaction where you can see the water has accepted the proton to form H3O plus. So strong acids, equilibrium lies well over to the right. So remember, they dissociate fully, and weak acids, equilibrium lies well over to the left. So you should be well drilled in this now. So we've gone through loads of different examples here of where equilibrium lies and how to determine if it's a strong or weak acid. It's going to be very important because you're going to need a lot of calculations later on. So that's why I said make sure your calculators are out for this bit. Yeah, so if you understand the basic concepts like that, then it makes it a lot easier to work out the parts later on. So, okay, so let's have a look. Look at some reactions of these, so actual chemical reactions. So acids react with bases to form salts, and they're pH neutral. So this is fairly straightforward. It's a fairly well-trodden path for this section, because you would have done it at GCSE, and even probably as far back as year 7, back when you started secondary school. So the H plus ions produced from acids react with OH minus ions produced from alkalis, and we make water which is neutral. So we can see here, we're going to add the A-level twist obviously to this as well, but you can see the H plus ions would be the acid, OH minus ions being your base, and that forms your water. So very basic, simple reaction. Where we say something's neutral, it means that the concentration, remember the square brackets means concentration of, so the concentration of H plus equals the concentration of OH minus. So here's a reaction. So this is hydrochloric acid, HCl, reacting with lithium hydroxide, which is your base, LiOH, forms lithium chloride, which is LiCl, and water, you can see, is at the end there. So salts are made from the metal from the base, okay, or the ammonium ion if it's an ammonium compound, and the non-metal, which is the other hydrogen, from the acid. Okay, so let's have a look. So you can see here we've got our non-metal from our acid, and the metal from our base form the salt that's produced. That's going to be important because you'll be given, obviously this is a simple example here, but you'll be given examples where you are expected to write the formula of a salt just from using the acid and the base that they've given you. So just be prepared for that. But you can see it's fairly straightforward. The rules are simple. Here's another example. Nitric acid reacting with potassium hydroxide to form potassium nitrate and water. So you can see here we've got our nitrate. This is the non-metal part of the acid, so in other words the bit other than the hydrogen, in this case it's nitrate, and the metal part of a base. React that together and we form potassium nitrate as our salt. And obviously we always produce water in these types of acid-base reactions, apart from ammonia, which we'll look at later. Here it is. So we see with ammonia, ammonia doesn't actually produce OH minus ions directly. It reacts with water first, accepts a proton, and produces ammonium ions and OH minus ions. So you can see here from ammonia, remember we looked at that just before, ammonia reacting with water, it uses the water to form your OH minus ions. So ammonia itself doesn't have OH minus ions, unlike your strong bases where they do. So let's have a look at that example that I said here with ammonia-based reactions. So you can see here that ammonia does react with acids to make ammonium salts, but it's the only reaction here that we need to know that doesn't actually produce water as part of a neutralisation reaction. So as long as you're aware of that, it's fairly straightforward. The rules are exactly the same when we're forming a salt, except with ammonia you just put NH3, obviously forms your ammonium, and then whatever's left from your sulfate. So you only form one product in this case here. Okay, so let's look at, since we're talking about neutralisation and acids and bases, we need to know some information about the enthalpy change of neutralisation. So remember, enthalpy is to do with the energy, like an energy change, similar to energy change. So it's an energy change of a reaction. So you can see here we get a change in enthalpy when neutralisation occurs. The only difference with enthalpy is the amount of energy per mole, whereas energy is just in joules. Enthalpy is the amount of energy per mole. So that's the main difference. So must emphasise that. I don't want you to get the two confused. They're not exactly the same as each other. But we get a change of enthalpy when neutralisation occurs. So the standard enthalpy change of neutralisation, let's look at the definition for this. So the enthalpy change when acid and base solutions react together under standard conditions to produce 1 mole of water. So pretty standard neutralisation reaction. So you've got obviously water's being produced and then your salt as well. So neutralisation reactions are always exothermic reactions. So enthalpy changes of neutralisation are always negative. So remember, enthalpy changes that are exothermic always have a negative value. So let's have a look. Weak acids and bases. So these dissociate weakly, so remember, and the OH and H plus ions are used up quickly in neutralisation reactions, as there's only a small number of them in solution. So remember, weak bases, they don't dissociate fully. And because of this, the acid and base are constantly dissociating to replace the H plus and OH minus ions that have actually reacted. So if you remember, this is Le Chatelier's rule about looking at equilibrium, that if you use up, in other words, in this case, if we lose some of the H plus and OH minuses to reactions, then they'll be replaced by further dissociation of your acid or your base. So the enthalpy involved in this type of neutralization is actually in 2 steps. There's the enthalpy of dissociation, which is actually to break the substance apart, the ionic substance apart, and then there's also an enthalpy when the OH- and H+ ions actually react. So the enthalpy of dissociation varies, and that depends on the acid or base that's being used, and this means that the enthalpy of neutralization of weak acids and bases, that varies too. So let's have a look at the strong acids and bases. So we looked at the weak acids and bases, let's look at strong acid-base reactions. So these dissociate fully, so we know that already, we've seen that, and they produce OH- ions or H+ ions into solution quite readily, there's a lot of them there. And the enthalpy involved in neutralization, so in neutralization reactions involving strong acids and bases, there's only one type involved here, and that is the enthalpy when the OH- and H+ ions react. So we've got one type of enthalpy change here. So unlike neutralization reactions in weak acids and bases, there's no enthalpy of dissociation enthalpy with strong acids and bases as they fully dissociate. Okay, so you've just got to remember that there's only one type here. So as a result, the standard enthalpy of neutralization is similar for all reactions of strong acids and bases. So that's quite an important point there. Okay, so let's look at the pH equation, and we're going to look at start looking at some calculations now. So the pH is a logarithmic scale that measures the concentration of H+ ions in solution. So remember, you've got a pH scale that scales from 0 to 14, 0 being really acidic, a very acidic substance, 14 being very basic, and 7 being a neutral substance, which is in the middle. So we're going to come on to that and how we link that in with these equations. So the equation we need to know to work out pH is minus log of H+. So here's a little bit of a thing to remember it. P means minus log, because you're going to see this later on. So if we imagine the P bit means minus log, and the H bit is the minus log of H+. So pH is basically the minus log of H ions. That's where pH comes from. So you can see here, this is a minus log of H+, and pH can be calculated when we know the concentration of H+ ions. So let's go through an example. So we've got calculate the pH of 0.03 moles per dm cubed of hydrochloric acid. So remember, hydrochloric acid is a strong acid here. So first point to note, hydrochloric acid is a strong acid, dissociates fully, and this means that the concentration of HCl equals the concentration of H+ ions, because we assume that all the H+ ions that are produced have actually come from our HCl molecule, and that fully dissociates. So that's a fair assumption to make. So HCl forms your H+ ions and your Cl- ions, as you can see down here at the bottom there. Okay, so using this equation, we can actually calculate the pH. So pH equals the minus log of 0.03. If you have a look on your calculator, you'll see there's a log button there. You just put minus and then just press that button. So it's fairly straightforward. You're going to see later on when the calculations get a little bit more complicated, what I've done is I've actually put in a picture of a calculator so you can see exactly which buttons you're going to press. I'm sure you'd be familiar with it, but it's just in case some people aren't, because some people maths may not be their strong point, and topics like this is probably a nightmare for people who might struggle with that. So just to break it down a little bit easier, just by showing the calculator and where the buttons are and familiarising yourself with it, but just put that in. But that'll be later anyway. So the pH for this reaction is 1.52. Okay, so check to see if that's sensible. Now in this reaction, you can see we've got a strong acid, so we'd expect a strong acid to have a pH of about 1.52. So that is sensible. If you're getting something like 9 or 10, clearly something's gone wrong, because you've got a strong acid. It's not going to have a pH of that. So just check, and there is reasoning behind the numbers. You're not just calculating these things for no reason. So the concentration of hydrogen ions can also be calculated when we know the pH, so we can effectively just flip the equation around. So we calculate the concentration of hydrogen ions of nitric acid with a pH of 1.7. So let's have a look. So all we do is we just inverse the pH equation. You can see here, this is what I was talking about with the calculator diagram. We just inverse the pH equation to give H+ equals 10 to the minus pH. So the reason why I brought in the calculator here is basically just so you can see what the inverse looks like. So all we do is we press the shift button in the top of the calculator. This is one of the traditional Casio calculators. So this is probably one of the most commonly used calculators. But if your calculator is slightly different, the principle is the same. I still have this as long as it's a scientific one. So you've got your shift button, press the log, and you see there's a 10 with a little box on the top. So that's just your you press that button. That on the calculator screen will come up with a 10, as you can see on there, and then it'll have the little flashing number in there. You just put minus the pH that you've been given. So in this case, it's 1.7. So we use this equation. There it is. H concentration of H plus is 10 to the minus 1.7. Using that button combination there, you can't just put in 10 in the calculator and then minus 7. It's got to be the shift log button. H plus is 0.02. So try that and see if you get the same answers. Okay, so let's look at sticking on the acid theme here. So some acids can donate more than one proton, and these are called polyprotic or polybasic. So let's have a look at nitric acid, as you can see here. So nitric acid is a monoprotic, or it's a monoprotic acid because it has one proton. So in other words, 1 mole of nitric acid will produce 1 mole of H plus ions. Okay. So you can see here, sulfuric acid is diprotic. So 1 mole of sulfuric acid will produce 2 moles of H plus ions here. You can also get monobasic and dibasic as well. So it depends on obviously what you've got attached to it. So phosphoric acid is triprotic. 1 mole of phosphoric acid will produce 3 moles of H plus ions. So that's going to be very important when we're looking at H plus calculations as well, or acid-base calculations later on when we're trying to work out the concentration of H plus ions. We've got to be aware of the acid, if it's monoprotic, diprotic, or triprotic, depending on how many H pluses there are, or H atoms there are in the molecule. Okay, so let's look at the calculation of pH of strong acids. So this is what we're talking about before, and this is why the mono, di, and triprotic comes into it. You'll see an example later on where that's going to become quite important. So when calculating the pH of strong acids, what we've got to make sure is we assume that they dissociate fully. It makes the math so much easier. So just assume that. So for monoprotic acids, so for example, HCl and nitric acid, so we've seen them before. So monoprotic acids, they dissociate to produce 1 H plus ion for every acid molecule. And this means the concentration of the acid equals the concentration of H plus ions. So for example, if we've got 1 moles per dm cubed of HCl, that will produce, and we assume that the number of H plus ions is the same, that produces 1 mole of H plus ions. So for example, the pH of 0.25 moles per dm cubed of hydrochloric acid is H plus equals the concentration of H plus equals the concentration of the acid. So therefore, when we use our pH equation, we can just use the same number. So that's 0.25 multiplied. So it's the minus log of 0.25. So put that into your calculator, and the pH is 0.6. Fairly straightforward. Gets a little bit more complicated with weak acids. We'll look at them later. So diprotic acids, for example, sulfuric acid, H2SO4, these produce 2 H plus ions for every acid molecule that we have. So it means that the concentration of acid is 2 times the concentration of the H plus ions that we've actually produced. So let's look at an example. So let's work out the pH, and we've kept the concentration to be the same. So we're going to work out the pH of 0.25 moles per dm cubed of sulfuric acid is 2 lots of H plus ions. Concentration of H plus ions equals the concentration of the acid molecule. So 0.25 moles per dm cubed of acid produces half a mole of H plus ions. So it's twice as many, because remember it produces 2 acids. So it's this number here that we're going to use in our equation, not 0.25. So that gives us a pH of 0.3. And again, with both of these, look at the numbers. You can see the numbers are 0.6 and 0.3. That is a strong acid. Now, that's what you would expect for molecules such as hydrochloric acid, nitric acid, sulfuric acid. Molecules like that, you would expect to see low pH values like that. If you're getting numbers like even 4 or 5, you've really got to just check, because 5 is a weak acid, and these are certainly not. Obviously, these are certainly not weak acids. These are strong acids. Okay, so similar to strong acids, so when we're calculating the pH of strong bases, make sure we assume that they dissociate fully. So, for example, we've got sodium hydroxide here that produces sodium ions and OH minus ions. And many strong bases, they dissociate to produce one OH minus ion for every base molecule. And this means that the concentration of the base equals the concentration of OH minus ions. So to do this, we have to use a slightly different equation to work out the pH of bases. And to calculate this, we still need the concentration of H plus ions. Even though it's a base, we still use this. And we use something called the Ionic product of water expression, which is Kw. And Kw is actually this formula here. So Kw is H plus times by the concentration of OH minus. So remember, this equation here is the one that you need to use if you are wanting to calculate the pH of a strong base. If it's the pH of a strong acid you're looking for, it's pH equals minus log times H plus ions, concentration of H plus ions. So this is only, we use this if it's a strong base. So to work at H plus, we need to know Kw, and we need to know the concentration of OH minus ions at a specific temperature. And once we know H plus, we can then work out the pH from that. So let's have a look at an example. So we're going to calculate the pH of 0.15 moles per dm cubed of sodium hydroxide solution at 298 Kelvin, Kw value of 1 times 10 to the minus 14 moles squared dm to the minus 6. You'll be given the Kw value, but Kw value has a standard value at room temperature and pressure of 1 times 10 to the minus 4. But you will be given, if it deviates away from that, you will be given that figure. So just try and remember that figure in particular. So first what we do is we substitute the figures into that Kw expression. So 1 times 10 to the minus 14 equals concentration of H plus times by 0.15. Okay, so we've just put in the value of Kw and obviously the concentration of OH minus ions as well. And we've got the concentration of OH minus ions from here, 0.15, because we assume that sodium hydroxide fully dissociates to form the OH minus ions that we need. Excuse me. So secondly, what we need to do is rearrange the expression to find H plus. Okay, so the concentration of H plus. So the concentration of H plus is 1 times 10 to the minus 14 divided by 0.15, and that gets you a concentration of 6.67 times by 10 to the minus 14. Okay, so we've got that. Obviously, the question did ask about pH, so this is where we bring that pH equation back in again. And there it is. So the pH is minus log of the H plus, because remember, we've got H plus now, we've just worked it out from the Kw equation there. So the pH of this is 13.18. Again, look at the number here. The number is 13.18. That actually tells us that this substance, it's got to be a strong base, because remember, 14 is a strong base, 13.18 is pretty strong, so that's fine, that fits. If you'll get numbers like 1 or 2, then clearly, something hasn't gone right. You just need to go back and check and just make sure that's that you've done you put your figures in correctly. Follow the same method, and you'll be fine. Okay, so let's look at Ka. It's an acid dissociation constant. Okay, so Ka is used when we have a weak acid. So we've looked at the equations for a strong acid. So remember, a strong acid is dead straightforward. We use that pH equation. But for weak acids, they only dissociate slightly, okay? And they do it in aqueous solutions. So we have to use another constant to work out their pH values, okay? So we can assume that the concentration of H plus equals the concentration of the acid for strong acids. But we can't do this for weak acids because they don't dissociate fully. So we use this other constant to work out the pH of weak acids, and we call this Ka. So weak acids exist in this equilibrium here. Now, with weak acids, equilibrium lies well over to the left. So you've got loads of HA ions. They're your weak acid molecules. You don't have many of these at all. So we're going to come up with a few assumptions here, because this will help us to calculate things. So we need to know these assumptions. So the first assumption is only a small amount of the weak acid, that's HA, dissociates. So what that means is we can actually assume that the concentration of HA at equilibrium equals the concentration of HA at the start. That's useful because in the question, if it gives you the concentration, it'll always be at the start, but we can assume that that is the case at equilibrium, so that means we can use it in our expression. Okay, so the equilibrium law can be applied here as we have an equilibrium reaction, okay? So we can use the Ka expression to represent the reaction on the basis of this assumption. So you can see here our Ka expression is always products divided by, products divided by our reactants, that's right, and therefore we can write our Ka expression. Now this is similar to your equilibrium expression because this is exactly the same. So if you've looked at, if you've watched the equilibrium topic, so that's topic 11, then I've done a video on that. Go and have a look there if you're not too sure on about equilibria. But this Ka is derived from the equilibrium expression as well. The second assumption that we make is that the dissociation of acid is greater than the dissociation of water present in the solution. Okay, so we can assume that all the H plus ions that are in that solution actually come from the acid and are not coming from any slight dissociation from water. So from that reason, we can then say that the concentration of H plus ions is equal to the concentration of A minus ions that's present in the solution as well. Okay, so we can now, with all these assumptions, we can now simplify the Ka expression, and we can simplify it to this. So Ka equals H plus squared divided by the concentration of HA. So much more simpler, and we use that to work out our acid dissociation constant, which obviously can then be used, all of this can then be used to work out the pH of a weak base. So weak acid. So let's have a look. So we use the Ka expression to calculate the pH of a weak acid. So calculate the pH of 0.0300 moles per dm cubed of ethanoic acid, so that's CH3COOH, at 298 Kelvin, and the Ka for ethanoic acid at this temperature is 1.76 times by 10 to the minus 5 moles per decimeters cubed. Okay, so we're going to write down the Ka expression. So that's the first thing that we do. So Ka is H plus squared divided by our concentration of ethanoic acid. So we looked at that. Excuse me. So we looked at that last time, and that's showing us the simplified equation that we've just seen before. And then we need to rearrange this equation to calculate H plus squared. So H plus squared is Ka times by the concentration of ethanoic acid. So the concentration, so H plus squared, therefore, if you put the numbers in, is 1.76 times 10 to the minus 5, multiplied by 0.0300, and we get a value of 5.28 times 10 to the minus 7. So that's the concentration of H plus squared. Now, that's H plus squared. We need to work out what H plus is. So what do? We need to take the square root to find H plus. So don't stop at that point. Keep going, okay? Because we need to work out the concentration of H plus. Don't forget that. So here we go. So here's the calculation for doing the H plus. So we take the square root of that value, and that gets us a concentration of H plus of 7.27 times by 10 to the minus 4 moles per dm cubed. So nice and straightforward, as you can see. So then once we've got that H plus, we can now use the pH equation. See, that's been brought in quite a few times in these steps here. So pH is minus log of H plus. Put all the numbers in the calculator, and we get a pH of 3.14. Again, check the number. Is that sensible? Yes, it is sensible because it's a weak acid, so we'd expect a weak acid to be around about pH 3 or 4 or somewhere around there. It's quite a strong weak acid, but it's still a weak acid nonetheless. So that's probably sensible. Okay, so we can use the Ka expression to calculate Ka or the concentration of a weak acid. So we can use it for both. Equations here. So what we need to do is look at this example, which is to calculate the concentration of methanoic acid this time at 298 Kelvin. It has a pH of 3.14, so they've given us the pH, and like in the previous example where we had to work the pH out. Now the Ka for methanoic acid at 298 Kelvin is 1.77 times by 10 to the minus 4. Alright, let's get stuck into this one then. So, first thing, we calculate the concentration of H plus using the pH equation. So pH equals minus log H plus. Rearrange that. We need to work out H plus. So remember, we do the 10 to the minus pH. So in this case, the pH is 3.14. So we do 10 to the minus 314 and 3.14. And we get our concentration of our acid, which is going to be 7.24 times by 10 to the minus 4 moles per dm cubed. So that's us got our H plus concentration there. So then we write down our Ka expression. Okay, so the Ka expression is Ka equals H plus squared divided by the concentration of our methanoic acid. And then we rearrange that equation to calculate the concentration of methanoic acid. Because remember, that's one of the things that we want to work out here. So there's our rearranged equation there, which is methanoic acid equals H plus squared divided by Ka. Put numbers in, and we get the concentration to be 2.96 times by 10 to the minus 3 moles per decimeters cubed. And then if we're going to work out the value of Ka, because that's the other thing we can work out here, it's much more straightforward. All we need to do is repeat steps 1 and 2, and then all we do is you just substitute the numbers into the expression here. So you can see we just put the numbers in here, and then we work out the value of Ka. We don't even need to rearrange it. That's the best type of question, isn't it? But you do need to know how to rearrange them, because they're not just going to give you some easy questions. They're going to give you some difficult ones as well to just test your knowledge. Okay, so let's look at the ionic product of water. Now, we looked at that briefly just before when we used it to calculate the pH of a base, a strong base. So we're going to look at a little bit more detail and what it actually means. So water actually exists in equilibrium. So when you have a glass of water, it doesn't just contain H2O. It actually contains H2O, H plus ions, and OH minus ions. So it contains loads of different ions in there. So this actually shows the expression for this. Now remember, in reality, it's not H plus ions. It is actually hydroxonium ions or hydronium ions, which is your H3O plus. As you can see there, that's the ion that you actually produce. But what happens, water actually exists in equilibrium. It produces these H3 plus ions and OH minus ions as well. So it produces quite a few of them. So it doesn't produce a lot of them, should I say. So the simplified version of this, remember you can simplify it, is H2O forms H plus and OH minus. So the equilibrium law can be applied here as well, because we have an equilibrium reaction. So we use that Kc expression that we've just seen to represent this reaction. So Kc, remember, it's the product divided by reactants. So the products are H plus and OH minus. Your reactants is H2O. However, water dissociates weakly into its ions, doesn't produce many ions. So in fact, there's so little OH minus ions and H plus ions compared to that water molecule that we have, that we assume that the concentration of water has a constant value, because it doesn't, it's a bit like, I use an analogy, if you have a millionaire and you give £100 to a millionaire, it's not really going to make much of a difference to that person's bank balance, because they've got £1 million. It won't be missed. But if you give that to somebody who has no money at all, then that £100 has so much more significance. So it's a bit like water. There's so much water around that any slight alterations in the amount of water is not going to make much of a difference. So we just assume that it's constant. So we need another expression to represent this quite unique property to water, and what we do is if we multiply the two constants, Kc and the concentration of water, then we get a new constant, which is Kw, and that's the ionic product of water that we've seen before. And it has the units of Kw always mole squared dm to the minus 6. And there it is there. And obviously that's the equation that you've seen before when we're working out the pH of a strong base. So this is where it actually comes from. This is why we call it the ionic product of water, because effectively it is water molecules and it's the ionic product of that, and it's just looking at the chemistry behind that. Okay, so there are some important points related to the value of Kw, and I briefly mentioned this before, but this is going to go into it in a lot more detail now. So the value of Kw is the same in a solution at a given temperature. Okay, so it's always the same, and it has that value that I said that you needed to remember, which is 1 times by 10 to the minus 14 mole squared dm to the minus 6. So this value changes if the temperature changes, so it's not fixed. So if you had a reaction and the temperature of it was you did it at 10 degrees and you did another reaction at 20 degrees, exactly the same reaction, the Kw values will be different because it is affected by temperature. So pure water has an equal concentration of H plus and OH minus ions. So in other words, what we can say is that the concentration of H plus equals the concentration of OH minus ions because they have there's the same quantity of each. Of course there would be, because the only, if we look at it in its pure form, of course, H plus and OH minus ions only can come from one water molecule. So if you're going to have an OH minus ion, you've got to have an H plus ion. So we assume that they are the same. And so therefore, when we're referring to pure water, we can simplify that again, and we can get Kw equals H plus squared. So chemistry is brilliant because it means chemistry always seeks to try and simplify everything as much as we possibly can. Take something that's really complicated and simplify it down, condense it down, just take all that rubbish out and just keep it as simple as you possibly can. The difficult bit is just trying to understand it and making sure, knowing where it comes from. I think if you have an appreciation of where it comes from, then it kind of makes it a little bit easier about, understanding what it is. If you know what it means, then it becomes less about remembering and more about applying it. And that's where you get your marks. Okay, so still sticking on Kw. And looking at some of the important points about Kw. So the value of Kw is the same in a solution at a given temperature. Okay, so it is the same there. So Kw, like say, has this value of 1 times by 10 to the minus 4. Sorry, I think we've... oh, no, we haven't. I thought I'd put the same thing in there. So pure water, like it says, it has that concentration of H plus and OH minus ion. And obviously we can simplify it as we've seen before. But pKw is actually calculated from Kw, and it is calculated using the following. So we've got pKw equals minus log Kw, and therefore Kw is the 10 to the minus pKw. This is very similar. In fact, it's the same principle to do with pH as you've seen before. So it's nothing significantly new here. We're just adapting it to something a little bit different here. And pKw is used to display Kw values on a smaller scale, which makes it a lot easier to use. So when we take a logarithmic scale, it means that we still keep the proportionality right, but it means that if we've got massive numbers, say going into millions and billions and trillions and etc., and we have some values that are at 1 and some values that are really high, you're going to have a graph that's just massive. So taking a log of either of them, it means we can condense that graph into something a lot smaller scale, but still keep the relativity of each of the points. So that's why we use log scales, but if you do maths, you'll know that anyway. Okay, so let's look at how we can calculate a pKa. So pKa is another way of measuring the strength of an acid. It's very similar to pH, but the lower the value, the stronger the acid. So pKa is taken by doing the minus log of Ka. Again, very similar to pH and pKw, and pKa is just looking at the Ka, so it's the minus log of Ka. So we calculate the pKa value for an acid with a Ka value of 7.52 times by 10 to the minus 3. So let's do this. Let's try and work this out. Very straightforward. pK is the minus log of Ka. So in this case, Ka is 7.52 times by 10 to the minus 3, as you can see there. And so therefore the pK is 2.12. So let's do it the opposite way. So Ka equals 10 to the minus pKa. So let's calculate the pH of 0.024 moles per dm cubed of ethanoic acid. This is at 298 Kelvin. And this has a pKa value of 4.75 at 298 Kelvin. So the first one, we need to calculate Ka. So Ka equals 10 to the minus pKa. So Ka equals 10 to the minus 4.75. And so therefore Ka will equal 1.78 times by 10 to the minus 5. So remember, to work out the 10 to the minus pH, we press shift and then log, and then you get the 10 with a little box above it that's flashing. And then what you put in that box is you put in minus your pKa value that you've been given in your question, or you may have worked it out in a previous question. Okay, so let's look at so that's calculating the pKa, obviously, in this case. So then we need to calculate the H plus from the Ka expression. So remember, Ka is H plus squared divided by your ethanoic acid in this example here. So H plus squared equals Ka times by your acid, which is these figures here. H plus squared is 4.45 times by 10 to the minus 7. And then obviously we've got a squared value there. So to work out the concentration of H plus on its own, then we need to take the square root of that figure that we've just worked out. So that gets us 6.67 times by 10 to the minus 4 moles per dm cubed. So now we've got the concentration of H plus. We then need to work out the pH of this. So we bring in our pH equation back again. I told you it keeps coming back, so you've got to remember this equation. So calculate the pH minus log of H plus. Whoops. Put the figures in, and then you get a pH of 3.18. Sorry, I've just dropped my pen there. Getting all excited about pH. Right, okay. So pH is 3.18 in this example. Again, check to see if it's right. Ethanoic acid is a weak acid. We would expect a pH around that figure. It's quite, like I say, it's quite a strong weak acid, but we'd expect it around that area. Now, one thing, and this is really going to be emphasized a lot more later on, but you'll notice, see this equation here, where we're using KaH plus and your ethanoic acid underneath. So this is fine, and this is a good assumption to make when we're working out the, say, the pH or the pK or Ka of a weak acid. But this equation is not really used when we're using buffers, and we have to actually not assume the H plus squared bit, but I'll come on to that later on. I just thought I'd mention it now, just to emphasize that point as many times as I can throughout the video. Okay, so how do we measure pH experimentally? Okay, so obviously we know how to calculate it, but how do we actually get a chemical and then say, right, well, this has got a pH of this? Okay, it's very straightforward, actually. We use pH meters. Now, what we've got to make sure, though, with a pH meter, if you've used a pH meter at school or college, wherever you're using, wherever you have access to a lab, then if you put it into a pH solution, it may not be calibrated properly. It's a bit like scales, where if you're weighing out stuff to make a cake or something, or you're weighing yourself, you've got to make sure that the scales are on zero, the balance is on zero first. If it's not, then it's not going to show an accurate or true value of what that is. So in this case, we need to do exactly the same with a pH meter, but we can't just press a button and press zero. We've actually got to do some chemistry with it. Of course we have. So a pH probe must be put in distilled water first, and the meter reading should be pH 7, and we adjust it if it's not. So put it into pure water, and you'll have a solution which is pure. Stick it in there. If it's not 7, adjust it. You can see we've got a picture of a pH meter there, showing the measurement of tap water in this case. So when we've done this, we then need to repeat it with standard solutions at pH 4 and pH 10. So one slightly acidic and one slightly basic. What we've got to do is rinse the distilled water, rinse the end of the pH probe with distilled water between dipping it into pH 4 and pH 10. And so these solutions are what are called buffer solutions. We'll come into this later on. But basically, they're very precise. We can rely on them being pH 4 and pH 10. So you might think, well, how do you know it's pH 4? We make it as a buffer solution, but we'll come on to that later because you do need to know about buffers. So the pH meter should be calibrated for use, and we've got to wash it. The reason why we've got to wash it is you'll contaminate your sample. So what we want to make sure is that if we've dipped it in a solution of pH 4, we want to make sure everything is washed off that first, turn it back to neutral, then put it in pH 10. It's a bit like if you're cutting chicken, for example, you wash your hands. You don't then cut your chicken and then immediately handle something which is like a fresh food, otherwise you're going to contaminate it. It's exactly the same with chemistry. There's a lot of links between cooking and chemistry or baking and things like that, which I quite like because I like baking. Okay, so let's have a look, see how we can understand pH. So obviously we can measure the pH. We now need to know if it's an acid or a base, and if it's a strong acid or a weak acid. So we need to be able to identify this. And here, what we're going to do is we're going to compare equimolar, so it's the same number of moles of each of these substances. And we're going to analyze if it's an acid or a base, if it's strong or weak. Okay, so let's have a look at a strong acid. So we're going to use 1 molar of hydrochloric acid so pH of 0. If we use H plus equals 10 to the minus pH, so the concentration of H plus is 1 mole per dm cubed, HCl has to be a strong acid as its concentration of H plus is 1. Okay, very, very important. That's how we can identify if it is a strong acid. So let's look at a weak acid. We take the same concentration, okay, of methanoic acid here. This is a pH of 2.4. Put in our calculate the concentration of H plus, and we get this value here. Now CHOH has to be a weak acid as its H plus concentration is 0.0398 rather than 1. So 1 would signify that it dissociates fully. Anything, the further away it is from 1, the weaker it dissociates. And obviously we can see here that the concentration of H plus is partially dissociates. Both producing H plus ions, 1 H plus ion per molecule to keep it fair, but you can see that the weak acid is not producing nowhere near as many H plus ions as the strong acid. Neutral substances, so these are green. You notice the color coding here for the pH, your pH tape. So neutral solutions, 1 molar of sodium chloride, this is a salt which we know is neutral, has a pH of 7. You put it into the figures here, H plus 10 to the minus pH, concentration H plus is 1 times 10 to the minus 7. Sodium chloride has to be neutral as the concentration of H plus is 1 times 10 to the minus 7. What this means is the concentration of H plus equals the concentration of OH minus ions. They're exactly the same. So remember, Kw, this is the ionic, this is the equation for pure water, is 1 times 10 to the minus 4. So that means that these two figures here must be 1 times 10 to the minus 7. So that means it must be neutral. So that's how you can tell if something's neutral. A weak base, so 1 molar of ammonia is 10.6. That is a pH of 10.6. Put it into our equation, do exactly the same. Okay, and we get this value, 2.4 times 10 to the minus 11. This is the concentration of H plus ions. Ammonia has to be weak base because its H plus ions is 2.4 times 10 to the minus 11. And this means that the concentration of OH minus ions that's in there is 4.2 times by 10 to the minus 4 moles per dm cubed. Okay, so that tells us that actually this figure here, if we do it on a scale up to 14, this tells us that actually there isn't a massive amount of OH minus ions. This will become more apparent when we compare it with a weak base, and you'll see what it means. So you remember that the value of Kw is that, and the Kw, the value is 1 times 10 to the minus 4. So remember, this doesn't have many OH minus ions, so it's not going to be, it's got more OH minus ions than H plus. This is what it's telling us. If we subtract these two figures away or divide them, then we get them, obviously we get the amount of there. So this is more, this is easier to compare when we compare weak with a strong base. So a strong base is sodium hydroxide. 1 moles per dm cubed of sodium hydroxide gives us a pH of 14 because it's a strong base. Put the figures in, and the concentration of H plus ions is 0 because a strong base, we would assume in a perfectly strong base, we assume there's no H plus ions at all because it is wholly basic. So we would expect a concentration of H plus ion to be 0. So it's a strong base. Its concentration of H plus ions is 1 times 10 to the minus 14. What this means is the concentration of OH minus ions is 1 mole per dm cubed. So in other words, we've got loads of OH minus ions but no H plus ions. And basically it's a scale. So if we go from 0, so strong acid has a concentration of 1 H plus and a strong base has none. So we're going from 1 to 0, and all the numbers in between, these numbers here, are numbers which fit in between that scale of 1 and 0. Okay, so that's all it is. It's a very, it's like a sliding scale, and obviously a neutral solution will have an equal number of H plus and OH minus, whereas a strong acid will have a lot more H plus than OH minus, and a strong base would have a lot more OH minus than H plus in solution. So this is all this is demonstrating, is the relationship between H plus ions and OH minus ions. Okay, so what we can do is we can use the mass and pH from experimental data to actually calculate the Ka that we've just seen before. So let's look at an example. So calculate the Ka of a solution made from 1.2 grams of methanoic acid, which is HCOOH dissolved in 250 centimeters cubed of water with a mass, dissolved in 250 centimeters cubed of water with a pH of 3.14. So let's go through this example. So the first thing we need to do is calculate the number of moles of methanoic acid in solution. So moles equals mass divided by M. Moles is 1.2 divided by 46, so 1.2 being the mass. This is the mass of methanoic acid. 46 being the, obviously this would be the molecular mass of your methanoic acid. And this gives the number of moles to be 0.026 moles. So then what we need to do is calculate the concentration of methanoic acid in this solution. So we worked out the moles, then we need to work out concentration. So concentration is moles divided by volume, must be in deciliters cubed. So here we've got 0.026, which is the number of moles that we just worked out there, and the volume is 0.250. Remember, they've given us this in centimeters cubed, well, 250 centimeters cubed. So we need to convert that to deciliters cubed. We divide by 1,000. That gets us a concentration of 0.104 moles per dm cubed. So that's the concentration of methanoic acid in our solution. So then what we need to do is calculate calculate the concentration of H+. So we use that pH equation again, so it's coming again, you see. So pH equals minus log H+ ions. Rearrange that to get 10 to the minus pH. So therefore we have a concentration of H+ ion for methanoic acid to be 7.24 times by 10 to the minus 4. Okay, so now that we've got our concentration of H+, we can now finally calculate the Ka. So use the Ka expression. Ka expression is H+ squared divided by your methanoic acid, concentration of methanoic acid. So therefore Ka is 5.04 times by 10 to the minus 6. And then once we've got that, we need to work out, we need to remember that your acids, the concentration of HA at the start equals the concentration of HA at equilibrium. Okay, so that's the assumption we make for weak acids, because remember that they don't dissociate fully. So even though they've given us the concentration at the start, it's exactly the same as what it is at equilibrium. Okay, so let's have a look at acid dilution and pH. So what this is doing is basically giving a little bit of an understanding about the logarithmic scale and what it means when we're diluting acids and bases. So diluting acids will reduce the concentration of H+ ions, and that in turn increases the pH. So remember, pH is decided upon on the concentration of H+ ions. So if the concentration is lower, then we're going to have a higher pH, obviously. So strong acids, let's look at hydrochloric acid first. So if we dilute a strong acid by a factor of 10, then the pH will increase by 1. So remember, the concentration of H+ equals the concentration of your acid. So remember that. Okay, so whatever that is, because it's a strong acid, we can make that assumption. So let's have a look. So if we've got an acid concentration of 1, okay, and then we have a pH of 0, so that's fine. But if we dilute that down by a factor of 10, so we have 0.1, then the pH will increase by a factor of 1. So that'll increase to 1. Diluted again by another factor of 10, and we get a pH of 2, and so on. So you can see here the dilution factor, we have to dilute it by 10, and that will change the pH by 1. So you can try this. If we substitute all of this data into the pH equation, we can actually prove that actually the pH does change by that value. So have a go. Weak acids, so let's look at, for example, ethanoic acid. So if we dilute a weak acid by a factor of 10, then the pH will increase by 0.5. So it's not quite the same ratio as what it is for a strong acid. So using the same factor, so you can see here we've got our acid concentration here, which is 1, and let's just bring this in, so that acid concentration is 1, and the pH of our ethanoic acid here in this example is 2.5. But if we dilute it to 0.1, okay, so we increase the factor by 10, then the pH only increases to 3, so only increases by a half. Okay, so again, try and substitute this data into a rearranged Ka expression. Remember, we've got to use the Ka expression because these are weak acids. So if we put it in here, so Ka H plus squared over the concentration of the acid gives H plus equals the square root of Ka of the acid. So therefore, what we can say is the pH is the minus log square root of Ka concentration of the acid. So it's just a way of testing, just to prove that actually that this is the actual scale to do with weak acids, about how it changes. If we change the concentration, we actually change the pH by half. Okay. So let's look at titrations. It wouldn't be acid-base without doing titrations with it. Now, you might have done these in school and college, and there might be you either absolutely hate them and really don't get much results from them, or actually you're quite methodical and accurate, and you actually don't mind them. You find them quite therapeutic. So titration, these can be used to work out the concentration of an acid or a base. So you can see here, we've got our setup here. We've got our burette, and in this example, we could either have an acid or a base in the burette, and it has a known concentration, so we know that bit. And we have an acid or a base with an unknown concentration, but a known volume in this conical flask. And what we do is you add a few drops of indicator in there as well. So the indicator tells us the end point. And then what we're doing is we're going to add the chemical in the burette to the conical flask until the indicator changes colour. This is known as the end point, like I say. And we've got to do it drop by drop. So we've got to be quite careful with this, really. So if we don't do it drop by drop, it can take one drop to reach the end point. But if we don't, we could either add too much and miss the end point, or we don't add enough. You probably wouldn't not add enough, because you would stop when you get a colour change. The main risk here is if you add too much and you miss the end point. You want to get the end point absolutely spot on. So drop by drop is really important. Now what we do is once we've done that and we've got that change in colour, then what we need to do is read how much chemical was added from the burette to neutralise the chemical in that conical flask. And we always read at the bottom of a meniscus. So the meniscus is this bubble here, and you can see that's the bottom there. So this one, as you can see here, is reading 20 centimetres cubed, not 19.8, which is what it would read if you read at the top of the meniscus. And then what we need to do is record your results to 2 decimal places. Repeat your results until you get 2 concordant results. That means that the results must be within 0.10 centimetres cubed of each other. If they're not, then you're not going to get an accurate result. So, for example, if you do 3 or 4 different titration runs and you get 20, 25, 22 and 19, then neither of them are concordant, and which one is actually right? So if you're getting them that varied, then something's definitely wrong. So you should be within 0.1. So always repeat. As long as you got at least 2, that's enough, and then you know which figure you're going to use in your calculations. Okay. So what we're going to do, obviously we know what a titration is and we know how that works. And what we're going to do is look and see what we get if we plot the results. So if we had a pH meter in our conical flask instead of an indicator, and we're monitoring the pH as we're adding our solution, depending on what that is, into our conical flask. So what these graphs are going to show us is going to show us the pH against a volume of base added from a titration. So in this case, we're going to add a base from the burette, and they show different combinations of weak and strong acids and bases. So we're going to look at each example, and you need to be familiar with the shapes of these curves here. So let's look at a strong acid, strong base first. So key things you need to look at for these graphs here. This is starting at 0, close to 0. So this is telling us that in our conical flask we have a strong acid here, and we're adding a base to this, because as time goes on, what's happening is this is becoming increasingly more basic because we're adding a base to the acid in there. Now this is a strong acid, strong base, so we start really low for a strong acid, and then as we add our base, it becomes turns to a strong base there. So that's quite important. Strong acid, weak base, still starting at a low point because we've got a strong acid in our conical flask, but we're adding a weak base, so the end pH is not going to be very high because we're adding a weak base. So that's a classic sign of a strong acid, weak base. So make sure you know the shapes of these and understand what's happening. So weak acid, strong base. So because it's a weak acid, the curve starts a little bit higher up, so somewhere around about pH 5 or 6, but strong base, so you actually get an end, the end pH, should we say, after you've added all, will be somewhere in the region of 13 to 14, so it's going to be quite high. And then the final one is weak acid, weak base. Now you can see here we don't get a very sharp endpoint here, so not very good titrations. But you can see here that we've got a very high start point because we've got a weak acid, and the end point, well, the end pH, should I say, not the end point. The end pH here is actually a low value because it's a weak base. So you don't really get a very sharp endpoint, which is that vertical part there. So let's look at some of the extra features to do with these types of titration curves. It's a classic titration curve, this S shape here. So the straight line bit, the vertical bit, is the equivalence point or the end point. And at this point, the acid has been neutralized fully by the base. Excuse me. So the sharp vertical rise shows a rapid change in pH. Okay, so we've got a very sudden change here. So the change in pH is smallest when using weak acid and weak base together in a titration. We'd seen that in the previous slide there. We don't really get much of a jump with a weak acid, weak base setup. So in this example, with the blue lines you can see there, we start with a strong acid and add a base as the graph starts at pH 1. And you could actually start with a base 2, which shows in this blue line. So you can see here, if we start with a base in our conical flask, we start with a really high pH. If we start with a strong acid in our conical flask, we start somewhere down here. So they can go either way. In this case, this would be a strong base. We're adding an acid to it, and the pH drops towards an acidic solution. And this is vice versa. So just be aware, it can go either way, but the rules are still the same. So this is an interesting one. So at this point here, so halfway along the flat part at the start of your titration curve, is called the half neutralization point. And this is the point halfway between 0 and the equivalence point. And it can be used to calculate pK. So remember we looked at pK before. And it can be used to calculate the pK of a weak acid by taking the pH at this point. So that's really interesting. So once we've done the full titration, what we can do is then say, right, where's halfway along that line, and work out what is the actual pH of the substance. So the reason why we can do this is actually looked at deriving from an equation. So at this point, the half neutralization point, this is not the same as an end point, remember. So the half neutralization point, the concentration of acid equals the concentration of the base that's in that solution. So that's quite an important point there. So if we take the Ka expression, because it's in equilibrium, remember, H plus A minus over HA, because the concentration of HA and A minus at this point is the same, we can cancel them out. So there we are. So we can get rid of that. So then what we're left with is Ka equals H plus, the concentration of H plus at this point. So then if we take the minus log of both sides, okay, we get minus log Ka equals minus log of H plus. Now you might see that as quite familiar, and that's because pK equals pH. So that means that obviously we know that if the concentration of HA equals the concentration of A minus, that is effectively pK equaling pH. So whatever its value is there, the pK value, we can obviously work out the pH at that point as well. So that's important. You need to be able to work that out. You need to know how that's derived as well. So just be prepared to explain what's significant about that point and where it's actually derived from. Okay, so obviously we've looked at titrations. Remember we mentioned that you've got to add an indicator into your conical flask. And that indicator actually tells us where that endpoint is. And the endpoint is the vertical bit on the graph. But what we've got to do is choose the right one. There isn't just a one indicator fits all. Indicators change in different ranges. So a suitable indicator must change colour entirely in the vertical part of the titration curve. And this must do that because it must change in that point because that's the only way in which we can determine where the endpoint is. So in this example, we've got to have an indicator that changes colour completely between the range of pH 3 and pH 10. So There's a variety of different ones that we can use here. So the common ones are things like methyl orange and phenolphthalein. So here you can see the colour change of methyl orange is between 3 and 4.5. That's when it completely changes colour. And phenolphthalein is a colour change of pH 8.2 to 10. So we've got a colour change there. So methyl orange is red at low pH. This is an acidic solution, and yellow at higher values. This is when it's an alkaline or a base. And so it can be used ideally for strong acid, strong base reactions, or strong acid, weak base reactions. That's when it could be used perfectly for that. Phenolphthalein, on the other hand, is colourless at low pHs, so in acids, and pink at higher values, and it can be used for weak acid, strong base reactions. That's the ideal type of titration you do there. So you can see depending on the titration that you do will depend on which indicator you're going to use. So notice with weak acid, weak base titrations, they have no real sharp pH change. It's really difficult. So an indicator isn't suitable here because an indicator could change beyond the endpoint or before it, which is not really ideal. So what we really must do for these type of titrations is either not do them at all and try and avoid them because they're not great, or we use a pH meter and we plot a graph like this. Okay, so what we've got to do is look at titration calculation. This is just a reminder. You would have seen this already. It's just making sure that you understand how to calculate reactions to do with titrations. It's very straightforward. But remember, the equivalence point is the point at where neutralisation occurs. Okay, and what we do is we use a pH meter to plot the titration curve to find it. So let's have a look at this example here. So we've got 15.7 centimeters cubed of 0.450 moles per dm cubed of sulfuric acid was required to neutralize 0.120 moles per dm cubed of sodium hydroxide. We're going to calculate the volume of sodium hydroxide being neutralized in centimeters cubed. So here what we've done in this example is we're going to put sulfuric acid in our burette, which is here, and we're going to put sodium hydroxide in our conical flask at the bottom. So the first thing we have to do is write out our equation. With any type of titration, we write out our equation first. So we've got sulfuric acid, which is this bit over here, and that's going to react with sodium hydroxide, which is our base. It's going to form sodium sulfate and water. I always use saying, if you've seen my videos before, if in doubt, work out the moles. So in this case, we're going to work out the moles, and the reason why is if you know the moles, you can work out pretty much anything from that. So the moles of sulfuric acid is concentration down volume, if you remember that from year 1. So moles is 7.07 times by 10 to the minus 3. That's how many moles of sulfuric acid we have. Now, I put the times 10 to the minus 3 there because we have to convert our volume into decimeters cubed. Now, we've been given a volume here of 15.7 centimeters cubed. I find, if you've seen my videos, you'll see it as well, but I find it easier just to add times 10 to the minus 3 on the end, because that means the same as dividing by 1,000, and that allows us to convert from centimeters cubed to decimeters cubed. So then we use that equation that we've just written out there before to find out the molar ratio in order to work out the moles of sodium hydroxide. So we'll call it stoichiometry. So there is a 1:2 ratio between sulfuric acid and sodium hydroxide. So the moles of sodium hydroxide is 2 times the moles of sulfuric acid because we've got a 2:1 ratio. So sodium hydroxide is 2 times 7.07 times by 10 to the minus 3, which is going to give us 0.0141 moles. Then once we've done that, we can then calculate the volume using volume equals moles divided by concentration. So here we've got the volume in decimeters cubed, the number of moles that we've just worked out just before there, which is here, times divided by the concentration, which we were told about over here, and that's going to give us 0.118 decimeters cubed. Now, to get to centimeters cubed, we need to multiply that by 1,000, and that gets us at centimeter cubed, which is 118. So that should be multiplied by 1,000 because it's wanting us to work that out in centimeters cubed. Okay. Okay, so this is the last bit. Okay, it's a big topic. I did say that, and my voice is nearly gone. A buffer is something that we've seen already. Buffers are something that resists the change in pH. So we've seen a little bit in terms of the calibrating a pH meter, for example. It resists the change in pH when small amounts of acid or base are added. So that word resists is important. It doesn't stop the change in pH. It just resists it. Okay, it slows it down. Very important. So they don't change it. And there's two types of buffers that we need to know. One's acidic and one is basic. Okay? So, now with buffers, you've got, I think the key thing, so I'm going to mention this now before we actually dive into it. With buffers, we've really got to understand the mechanics of a buffer. Okay? Buffers are made up of two parts, so we'll look at that in a minute, but they're made up of two parts and they have two equations, and effectively we're just coinciding both equations together, and you'll see what I mean. You see what I mean in a moment. But the key thing with the buffer is you've got to know the equations to do with acids, bases, and the formation of salts. You've got to understand about equilibrium for this, and you've got to be able to use that Ka expression for the calculations later on. Okay, so I'll talk it through. So, acidic buffers resist the change in pH in order to keep the solution below pH 7, okay, because it's an acidic buffer, so it's got to keep it as an acid. And they're made from a weak acid and a salt of its conjugate base, okay, so that's very important. The weak acid and a salt of its base. It's important to get your language right in this, and while trying to explain how buffers work. So, an example is an acidic buffer is using ethanoic acid, there's your weak acid, and sodium ethanoate is its salt. So the salt must be formed from the acid that you're using. So in any buffer solution, like I say, there's two equilibrium equations at play, and the two equations coexist in the same beaker. So we have one beaker, but we have two equations. Okay. Now, buffers is probably one of the most complicated systems to explain at A-level chemistry. So if you can get your head around this and understand this, this is going to make it so much easier to explain the calculations afterwards. Okay, so I'll try and go through this as detailed as I possibly can. So you can see here is our weak acid, ethanoic acid. It dissociates and to form the ions and your ethanoate ions and H plus ions. We've seen that before. Nothing new there. Okay, they dissociate weakly. Equilibrium lies to the left. We've seen that before. There's nothing new there. Okay, we've got a concentration that's really high here and low concentrations of this. The reason why is it's a weak acid. Okay, so weak acid. So what we've got to make sure is that we understand how that works. Let's look at the salt bit, because remember, buffer is made from two bits, the weak acid and its salt. So we write the equation for a salt as well. So salt is this is sodium ethanoate. It dissociates readily. Okay, so you add salt to water and it doesn't put up any fuss whatsoever, mostly. So these types of salts here, you chuck it in water and it dissolves very easily. And when it dissolves, it produces these two ions here. Okay, so it fully dissociates. Equilibrium lies to the right. And so therefore, we don't have many fully salt particles here, full salt particles, but we have lots of the ions that have derived from that salt. Okay, so make sure you understand that bit. So there's nothing new there. It's all kind of what we've seen before. Okay, so what we've then got to do is we've got to try and explain what happens when we change the conditions of this buffer. Okay, now in the exam you've got to articulate yourself in a particular way. Okay, so you look at the words that I'm using here. The words will help to. And the keywords here will help to explain what's going on. And they will ask questions like this. So let's look at what happens when we add an acid, H+, to this buffer. Okay. So the H+ ions react with the ethanoate ions in solution. Why do they react with the ethanoate ions? I hear you shouting. The reason why is because it's a H+ and it's going to be attracted to something that's negative, isn't it? So it's going to react with the CH3COO- ions that are in here. There's loads of them in solution, thankfully, because we've got a salt that's produced them all. High concentration of these from the salt, and so therefore what happens is more ethanoic acid is produced, equilibrium shifts to the left. This is the complicated bit. You've got to see these two equations as one, okay? Even though we've written them separately, see them as one. And so what happens is actually you can see here that we've got our weak, we've got our ions here. The H plus ions react with that. And remember, equilibrium will shift to try and replace these back again. So what will happen is actually we form lots of acid here. So sorry, it's not equilibrium, that's in the next one. But what happens here is that these ions react with the H plus and we form our acid. Remember, the acid dissociates weakly, so we produce more acid here. Okay? So it's a bit like having, let's say if you have 100 people in a hall, okay? Each one of these 100 people represents a thanoate ion here. So you've got loads of them in a hall. You've got 100 of them that are lined up. And then we add some H plus ions, and let's say we add 10. Okay, we had 10 people in there. It's just a small amount, remember. So them 10 people will couple up with 10 of the people in the hall, and therefore you still have 90 people left in the hall, but all the acids that you've added have actually reacted with this salt, and now they're coupled up and they form as a couple. Okay, do you get that? So it's just trying to explain what's actually happening here. Okay, so let's look at a different one when we add a base to this. This is where the equilibrium bit does come in, okay? So we add a base, which is OH minus. We add it to this buffer. Remember, the buffer has both of these equations coexist in the same beaker. So the OH minus ions react with H plus ions in solution. Why do they react with H plus ions? Well, they're negative, so they're always going to go with a positive charge, aren't they? They're always going to be attracted towards a positive charge. Now, we do have H plus ions here, so we have them here, and we also have Na plus ions. But the Na plus ions will react with OH minus ions, and they'll just form sodium hydroxide, which is a strong base, and it dissociates fully. So what we'll do is we'll actually end up with OH minus binds back again. So it doesn't make any difference. So the one we're looking at here is actually the OH minus ions reacting with the H plus ions. Now, the problem is, this is like having a hall and we've got 2 people in that hall, because we don't have many of these whatsoever, okay? We've got 2 people in that hall, but we are introducing 10 people into that hall. Now, we've only got 2 H plus ions to react, and you may think, well, that's a problem, because we're going to be overwhelmed with people entering there. Okay, we've only got 2 people in that hall. So what we've got to do is we've got to get more people into that hall. So there's a low concentration of these. However, they can be reproduced from a high concentration of the acid. Remember, it's a weak acid. We've got loads of this, and this is a source of H plus ions. So this is where basically, if them 2 people in the hall are taken, and there's an excess of OH minus ions, then what we can do is we can chuck more people in the hall to pair up with them OH minus ions. We can replace the people who have been taken. And we call this Le Chatelier's principle. So remember, in chemistry terms, we are taking our OH minus ions, they're reacting with that H plus ions. Le Chatelier's principle says if we decrease the concentration of H plus ions, equilibrium will shift to replace them and put them back again, so it will shift to the right. So there it is. So it shifts to the right and it replaces them H plus ions. So you can see the mechanics of this are a little bit complicated. There's a bit of arrows flying everywhere. As long as you stick to that principle, just remember it. Try and visualize it as people in the hall lining up and people entering that hall to couple up with them atoms there. So this is what we're looking at here. So just try and remember that. If you get this bit, all the rest, I promise, the rest will be will make it a little bit easier. I think understanding how the mechanics of a buffer is really most of the problem. The calculations later on kind of fit around this theory here. Okay, so acidic buffers can also be made from a weak acid and a strong base. Okay, so this is going back to our titration that we've just mentioned before. So an example of an acidic buffer is using ethanoic acid, so remember that's your ethanoic acid, and sodium hydroxide. So let's have a look, see how this works. All of the base reacts with the acid in the following way. Okay, so we've got ethanoic acid plus OH minus ion, which has come from the base. This forms CH3COO minus and H2O, which is obviously water that's produced. So what we have is an excess of ethanoic acid. So we still have some left after all the OH minus ions have reacted. in our beaker we have a mixture of weak acid and it's salt and water. So let's go back to that hall analogy. We have 100 people lined up in a hall. It's like a dance hall. Let's say you've got 100 people lined up in that hall. We're going to put in, so the 100 people in that hall represent the acid. Okay, so they represent this bit, the weak acid. We're then going to chuck in some sodium hydroxide, and that's going to be, we're going to introduce 50 people. Okay, 50 people into that hall. So then 50 people represent the OH minus ion. 50 people will pair up with 50 of these molecules. So if you imagine, just picture that dance hall, we now have 50 paired up molecules. Okay, so we have our acid paired up with our base, that will form our salt. Okay, and we have 50 acid molecules unpaired. We have 50 ones that are not paired up. So in this beaker, we have a mixture of our weak salt and our acid. Okay, so you need to try and visualize that. So just imagine that. Okay, 100 people in the hall, 50 people come in, 50 are paired up, 50 are unpaired. So we have a mixture of salt and acid. Okay, my imagination, honestly. Right. So because there's still some weak acid in the remaining, it partially dissociates in the following way. So then molecules of weak acid are partially dissociating to form your ions that are produced there. Okay, so this is effectively a buffer. So we formed that buffer solution. So let's look at basic buffers, because I said there was two types of buffers. You've got an acidic one and a basic one. So basic buffers resist the change in pH still, but they keep the solution above pH 7, so they're keeping it basic. And so they're made from a weak base and its salt. So let's have a look at an example of a basic buffer using ammonia, which is NH3. That's the weak base. And ammonium chloride, which is NH4 plus Cl minus, which is its salt. So in any buffer solution, like say there's two equilibrium equations at play and two equations coexist in the same beaker. That's exactly the same as an acidic buffer. So let's have a look at the base bit first. So the base, remember ammonia reacts with water to form ammonium and your hydroxide ions. Because it's a weak base, it dissociates poorly. So we don't have many of these ions here, but we have lots of the ammonia that's over here. So equilibrium lies well over to the left. Now we need salt in existence as well. So the salt, like any salt, most salts, dissolve readily in water. So it dissociates completely. So we have large amounts of ammonium ions and chloride ions here, and low amounts of ammonium chloride, which is our base. So equilibrium lies well over to the right, and we assume that it's nigh on fully dissociates here. So what happens when we add a base to this buffer? Now just imagine, we looked at the example before with the acid, see if you can try and apply it to this as well. So we'll still go through it, but see if you can try and either pause the video and see if you can try and work it out and see if you've got it right. So what happens when we add a base, which is OH minus, to this buffer? So the OH minus ions, remember they're negative, they're going to be attracted to something that's positive. So in this case, it's the ammonium ions, NH4 plus, in solution. Okay, now there's loads of these from the salt. Okay, so that's fine. We've got loads of these and abundance of these. So we can add some OH minus ions, and as long as there's ammonium ions in there, then they'll react. And what they'll produce is more ammonia. They'll effectively form ammonia and water, and so that means that equilibrium will shift to the left. So we'll produce more of that if we add hydroxide ions. So that's fine. We've got loads of ammonium ions. Now, again, see if you work this one out. So what happens when we add acid, H plus, to this buffer? So pause it if you want to have a go yourself. So what happens when we add acid? So the H plus ions react with the OH minus ions in solution. Now you might say, well, hang on, there's a chloride ion there as well. There's a Cl minus. Well, if you think about it, that H plus, yes, okay, it'll react with the Cl minus, but that will form HCl, and HCl will dissociate fully back to the H plus and Cl minus ion. So it doesn't, HCl barely exists for any length of time. It just breaks down again back to square one. So the real reaction here we're looking at is the H plus reacting with the OH minus ions. Now the problem is we don't have many of these OH minus ions. So this is where Le Chatelier comes in. So have a think. So what do you think might happen here? So you can see there's a low concentration of these. However, they can be reproduced from a high concentration of NH3 and H2O. We've got loads of that. So they effectively put these OH minus ions back back into the system again. So this is Le Chatelier's principle. So we've removed some of the OH minus ions. Equilibrium will shift to replace them back again. Okay. So equilibrium shifts to the right, and that replaces them OH minus ions. So if you've really got the hang of this, and you kind of say, yeah, I understand this, the rest of it really is going to be fairly straightforward. There's calculations, of course, but the principle is, this is the key thing, it's just understanding what a buffer is. Okay, so let's link in titration curves and buffers. Okay, so we see evidence of buffer action in a titration curve. This is brilliant, because now we're linking this buffer action, which is kind of a little bit disjointed from everything. Well, not massively disjointed, but it's a bit separate, and linking it back into something which you've seen already. This is the magic of it. So remember, initially, right at the start, the pH changes quickly. Okay, so right at the start, it changes quite quickly. There's plenty of OH minus ions. Here we've got an acid in our conical flask, and we're adding a base to it. Okay, so here we've got loads of OH minus ions from the strong base. They react with the H plus ions to form your weak acid, so remember that. So here the curve becomes more level. We've got a flattening off, and this is because the buffer solution exists between your weak acid and your salt. So you've now established a buffer solution. Okay, and what this does is it resists the change in pH as more base is added, and so the curve is more level. So that flat bit at the start, this is why you get this funny shape, is actually a buffer action. It's not changing the pH. You're adding base to it, and you're looking at your pH meter, and it's like, well, it's not barely changing. That's because there's a buffer action going on here. Okay, isn't this quite clever? Right, so the flat bit, the vertical bit, here, this is when all of that weak acid is being used up, the equivalence point is reached, and the curve rises steeply. The buffer system now doesn't exist. So imagine this. I'm going to bring it back to this hall situation. You've got 100 people in a hall, okay? You're then going to introduce a person. This is like a titration. Introduce a person to that hall one by one, okay? So you've got person 1 in the hall pairs up, and that's that. You've got 99 left. Another person comes in, they pair up, you've got 98 left. And you keep on going and keep on going. You keep adding that base until everybody's paired up. And it's at that point, when you've got no more people left to pair up, you introduce one more person, okay, and then you've got an imbalance. You've got 100 people coupled up, and one person, which is like the OH minus sign, that's on its own. It's at that point, this is why you add it drop by drop, it's at that point that all of a sudden, bang, that pH changes. You've now no longer got a buffer. So any more hydroxyl ions you add in there, there's no change. Okay, there's no change in pH. And that bit, when everybody's coupled up and you add one more person in, is that vertical bit here. It's this bit here. Okay, now remember that half equivalence point that I was talking about? So that's where you have 100 people in the line. So half equivalence point was here, this bit here. Half neutralisation point, should I say. That's where you've got 100 people in the hall. You've introduced people one by one. And you get to a position where you've got 50 people that are coupled up and 50 people that haven't. So that's the half equivalence point. It's the end point where you've coupled everybody up, and there's one, you introduce another person, and there's nobody else to couple with. So that's how I imagine it anyway. You've got, obviously, you can't talk about couples in the exam. Please don't do that, because you'll not get any marks. Talk about it in the chemistry terms that you've seen on the screen here. So buffers have many uses, whether that is in household products or naturally occurring in living things. And a good example is blood. Okay, you might think, well, buffers, where are we going to use these? They're used everywhere, even in your own body. Okay, so let's have a look at how this works. So blood is vital, obviously, in our blood. It carries all the nutrients and substances and gases that we need to keep us alive. It has a pH of 7.4. Okay, now our system relies on a buffer system, which is carbon dioxide plays a big role in this, to effectively maintain the pH of 7.4. So when you think, we add substances coming in and out of the blood all the time. Sugar molecules, you've got hormones moving around in there, you've got gases, oxygen, carbon dioxide, we've got all sorts going on, and that anything like that can alter the pH. If your pH changes, then if you do biology, you'll know about this. If you get a deviation in pH in the blood, your cells don't work. Okay, they don't work as well. Enzymes don't work as well because they're pH sensitive, and so therefore you get organs that start to fail. You start to become tired because you're not using your energy efficiently. So there's loads of downsides if you're not getting the pH right. And so we use a carbonic acid, which is H2CO3, a carbonic acid molecule, and hydrogen carbonate, HCO3 system exists. So we have this buffer system here. So here we've got our acid dissociating to form our H plus and our ion. Okay, that's your weak acid. And also we have another system here to do with the carbonic system, forming your water, and carbon dioxide is also obviously present in the in our blood as well. And carbonic acid is controlled by respiration in your cells. So when you breathe out carbon dioxide, the level of carbonic acid reduces as equilibrium shifts right to attempt to replace them. So when we breathe out like this, yep. So I'm sure you know what breathing out is. That was stupid. So when you breathe out, carbon dioxide is expelled from your lungs, and so therefore equilibrium will shift to replace them carbon dioxide molecules. So effectively, it's the H2CO3 which will shift to replace them. So the amount of carbonic acid decreases. And so hydrogen carbonate, which is this bit here, HCO3 minus, is controlled by your kidneys, and excess is removed here. So if you've got too much of this, in here, then what happens is this is removed by your kidneys. So it's very, very delicate system. Okay, so I promised one to the last stretch here. So this is where we're calculating the pH of a buffer. So this is what I said about understanding the mechanics of a buffer. If you understand that, then you're able to actually get the calculations correct here. So to calculate the pH of a buffer, you need to know the Ka value and the concentration of the weak acid and its salt. So let's look at an example. I always find it easier to go through an example, and then you can see like a worked example, and then you can see what I'm doing. So we need to calculate the pH of a buffer that contains 2.35 times by 10 to the minus 2 moles of methanoic acid and 1.84 times by 10 to the minus 2 moles of sodium methanoate in 1 decimeters cubed of solution, and the value of Ka at 25 degrees Celsius for methanoic acid is 1.78 times by 10 to the minus 4 moles per decimeters cubed. So there's a lot of information in there. Okay, so what we're going to do is write the equation and the Ka expression down first. Okay, so the equation, here's our weak acid here. So our weak acid here, H plus and HCOO minus. Okay, and then we've got our Ka value here, which is H plus, HCOO minus, and HCOOH. So this is our products over reactants, remember. So notice in buffers, this is what I said earlier, that in buffers we don't say that the concentration of H plus equals the concentration of A minus, like what we do to calculate the pH of a weak acid. So we can't use this equation here. So effectively, we're using the old equation before we do this. We're using this equation where we still have the dissociated product of our acid in there. The main reason why we can't use that is because these here, this actually is derived from the salt, which we know there is some in there, so there isn't a balance because we've got another chemical at play that's producing this. So we must use the equilibrium concentrations here, not initial concentrations. That's very important. So that's another assumption that we can't use here. And note that we assume salts dissociate fully and weak acids dissociate poorly. So what we can deduce from that is effectively the concentration of the salt is represented by A minus. So that's this bit, okay? Because remember, that's coming from the salt, and the concentration of the acid at the start is equal to the concentration of that acid at equilibrium, because that assumes that the acid doesn't dissociate fully. Okay, so these are the assumptions that we're making here. So what we're going to do is rearrange that expression to get the concentration of H plus ions. Okay, so H plus, concentration of H plus equals Ka times by your concentration of methanoic acid divided by your methanoate ions, which are here. Okay, so we've rearranged that to get H plus as the subject. So note we have the number of moles in the question. Okay, but concentrations must be used. We've got to use concentrations. So concentration, remember, is moles divided by volume in decimeters cubed. But in this example, it is moles divided by 1 decimeters cubed. So here we are just going to use the mole values, the number of moles here, as the same as the concentration, because the volume that they're in is 1 decimeters cubed. So obviously if we take the number of moles here divided by 1, we're just going to get the number of moles, but you must use concentrations, not moles. So here we're going to use the figures that we've got here to work out the concentration of H+, and that's going to give us 2.27 times by 10 to the minus 4 moles per decimeters cubed. And then what we can do is calculate the pH of our buffer here. So calculate the pH. pH equals minus log H plus. Again, you can see that's come back again. Minus log of 2.27 times by 10 to the minus 4. That gives us a pH of 3.65. So you can see here it's not too dissimilar to what we've seen before. The main difference here is we've got to not use this equation here. We've got to keep the two different components in, and obviously take into account the assumptions that we're making as well. Okay, so what we need to do is look at, and obviously we know how a buffer works and the mechanics of it, but what we've got to be able to do is know how to make a pH or a buffer with a certain pH. So for example, I might want to make a buffer with a pH of 4. How do I make that? How much weak acid do I have in there? How much salt is required as well? So I need to know what I need to make, what I need to do to make this. Okay, so we use something called a Henderson-Hasselbalch equation. Okay, and this was actually developed by two chemists one was called Lawrence Joseph Henderson, and he was an American who come up with this equation, and the other one was Carl Albert Hasselbalch, who was Danish. And it was these two chemists who basically came up with this fantastic formula. It looks horrendous, but I'll simplify it. Again, remember, chemistry is all about trying to simplify some of these equations, because why make it complicated? He basically came up with these equations to calculate what pH, what would you need to make a buffer of a certain pH. So it's quite useful. So let's look at this equation first. And then we'll look at an actual worked example on the next slide. So this is the equation that he came up with. Don't be frightened, okay? You'll see how it fits later. It's fairly straightforward, so it's not too bad. So you can see here that we've got a pH equals pKa plus log to the base 10, and then we've got A minus and HA. So this is the concentration of our salt, remember from the previous slide to do with buffers, and this is the concentration of our acid. And this equation assumes that the concentration of the acid is equal to the concentration of the acid at the start of the reaction. So in other words, this is a weak acid, so it dissociates very poorly, so we just assume the concentrations are the same. And it also assumes that the concentration of A minus at the start is approximately equal to the concentration of A minus. So whatever the reagents are at the start, these are the assumptions that we're making here. Okay, and so remember for the pKa bit, because you're going to see this later, pK is minus log of Ka. So just a reminder on that bit as well. Okay, so what I've done is I've dragged that equation, the Henderson-Hasselbalch equation, at the top here. Okay, which is the bit here. So we're going to use that. So let's have a look at a specific example. So a buffer is created from methanoic acid and sodium methanoate, which is 0.8 moles per dm cubed of salt was used. What concentration of methanoic acid is required so the buffer has a pH of 3.9? The value of Ka at 25 degrees Celsius from methanoic acid is 1.78 times by 10 to the minus 4 moles per decimeters cubed. All right, okay, so let's have a look at this. So first of all, what we need to do is work out the pKa bit. That's why I put that bit on the slide first. So pKa is the minus log of Ka. So pKa is minus log of 1.78 times by 10 to the minus 4. That gives us a pK value of 3.75. Again, that's to be expected. It's a weak acid, so that's fine. Okay. So then what we need to do is we need to substitute the figures, because we've got the pKa bit. Okay, so remember the pKa bit is in your Henderson-Hasselbalch equation. So substitute the figures into the Henderson-Hasselbalch equation to get the ratio of A minus to HA. So that's the first thing, is we need to work out the ratio here. So what we're going to do is just put the numbers in here. So bear with me. You might look at this in a different way. You might have used a different method. Again, this is a method that I use to try and keep it methodical and try and keep it clear and simple so that you can see it. But you might be able to do it in a slightly different way. But 3.9, okay, is the pH side. So 3.9 has a pH of 3.9 equals 3.75, which is this bit, is the pK that we've just worked out here. So that goes in there. Plus log A minus HA. So the A minus is the ethanoate ions that comes from the salt, and this bit obviously comes from the acid. This is the ethanoic acid. So that's the first thing that we need to do. So then what we need to do is then flip it the other way around. Okay, so we get the log and this ratio here, because we need to work out the ratio. Remember, this is the ratio here. It's just represented as a fraction, but it's still a ratio, equals 3.9 minus 3.75, and so that gives us 0.15. So effectively, this ratio here, the log of this ratio, equals 0.15. So that's us worked out the ratio there. So to simplify this further, we have to remove the log 10 bit, because that's just ugly. We don't want that bit there. So the log 10 bit, and we do the inverse. This is 10 to the ratio, which we've just worked out there, which is 0.15. So here we go. Here's our calculator back again. So remember, to do the ratio, we just do shift and then press log, and that gets us the 10 with the little flashing box next to it. So all we do is you put 10 and then 0.15 into our calculator, and then we get our ratio. This ratio here equals 1.41. Okay, no logs in there, nice and simple. Then we know salts fully dissociate, so the concentration of the salt equals the concentration of A minus, which is obviously in our equation, and we then calculate HA equilibrium as it's equal to the concentration of HA at the start, remember, because it's a weak acid. So we then put it into our equation. Okay, so we know the concentration of the salt, because we've been told here, is 0.8. So it's 0.8 divided by concentration of acid, which we want to work out, equals 1.41, which we worked out here. We rearrange that equation, and we get concentration is 0.8 divided by 1.41, and so therefore the concentration of our weak acid is 0.57 moles per decimeters cubed. So you can see there's a lot of different aspects there. We've just got to make sure we're doing it in a methodical way. Work out your ratio first, simplify it by taking the inverse log, and then once we've done that, then we can actually work out the concentration of what we need to know, and then we can now make our buffer, which is marvellous. Okay, so wow, that was a marathon. So that's it. So that's everything on acid-base equilibria for topic 12 that you need to know for EDEXCEL. Like I said, there's a full range of videos on here that cover everything for EDEXCEL. You can dip in and out of the videos as you please. Obviously, there's a lot in there. It's a whole topic. They're all for free. All I ask is you hit the subscribe button. That'll be fantastic. And it just shows you support for the channel. As long as I keep getting the support, I'll just keep making the videos. And I'll keep them all free as well, because I think that's quite important, that anybody should be able to have access to these. I think that's quite an important point. But like I say, if you do want to have your own copy of these, you can click on the link. You can print them off and do whatever you want with them. Click on the link in the description box. You can get a hold of them there. You can purchase them from my test shop. But other than that, that is it. I hope your head's not hurting too much. Like I said, there's a lot of funny names in there. And a lot of quite complicated calculations, but I hope it's helped clear some of that stuff up anyway. Okay, that's it. Bye bye.